For the second example, I would really like you to pause the video and try to work it out first. You will have to, at some point, define a function that is described but not defined explicitly in the prompt. So pause the video, try to work this one out, and then rewatch it at the end, and I'll go through this one a little more quickly. So water is being pumped into a tank at a rate modeled by W. So W is representing the rate at which water is pumped into the tank, and that's measured in gallons per hour. So T obviously represents time and is measured in hours. And again, we're given W of T in our graph. We are also told that at time T equals 4, there are 40 gallons of water in the tank. So that's not a rate. That's not W of 4. That's the amount of water in the tank. I'm just going to write that out to the side. So amount of water in the tank. So what's the value of W of 4? Well, if we go up to our graph, W of 4 is 3. Explain using correct units what that means about water in the tank. So when we explain in context, we would say at T equals 3 hours. And then if we think, well, what is W? W is the rate at which water is pumped into the tank. So at T equals 3 hours, the rate at which water is pumped or is being pumped into the tank is 3, and then we've got to use our units, gallons per hour. Okay, in part B, what is the value of W prime of 6? So if we're looking at W in my graph, I know W prime, the derivative, is also the slope of the tangent line. But at 6, since that piece is linear, it's not a tangent line, it's just the slope of that line. So we have to find the slope of the line at 6. And if I pick 2 good points, I could say I'm going down 3 and to the right 2. So my slope is negative 3 halves. So W prime of 6 is negative 3 halves. And if we explain what that means, well, we know that the derivative is a rate of change, but it's the rate of change of another rate. So we really want to avoid saying something like the rate at which the rate of change is changing. Do not do that. It's technically the truth, but don't do that. So here's how I would write this. I would say at T equals 6 hours, so we have to include our units, the rate at which water is pumped into the tank. So in all of those words, I just described W. So if I think about this, W prime of 6 tells me how W is changing at 6. So W, the rate at which water is pumped into the tank, well, I could either say is changing or I could say is decreasing, since my rate is negative, by, if I say decreasing, I'm just going to say 3 halves here. If I say changing, I would say negative 3 halves. So by 3 halves, and then I need the correct units, which is going to be gallons per hour squared. So if W is measured in gallons per hour and time is measured in hours, then W prime is gallons per hour, or gallons per hour squared. All right, part C. What is the value of the definite integral of W over 4 to 7? And explain using correct units. All right, so let's evaluate that first. Okay, so from 4 to 7, if I look at the area, this is a triangle 3 by 2, so 3 times 2 times 1/2 is just 3. And then from 6 to 7, we have this little triangle. Now I do need to kind of use the slope here. I can't guess, like if my rate of change is down 3 over 2, well, if I'm moving over 1, then I'm going down by 3/2. So 3/2 times 1 times 1/2 is 3/4. Oops. So 3 over 4 is the area of that little triangle, or 0.75 if you prefer to use a decimal. Okay, so since the area above the x-axis is positive, below the x-axis is negative, we get 3 plus negative 3/4, which is 9/4. Okay, so that's the value. Then when we explain, we've got to use correct units and talk about what that means about the tank. So this has to do with the amount of water in the tank and how that has changed. We said we can call that displacement. So remember that when we integrate, we are essentially multiplying and we're finding areas. So if W of T is measured in gallons per hour, and time is measured in hours, then when we calculate or compute that definite integral, our units are going to be gallons. So how I would explain this is I would say between time t equals 4 and t equals 7 hours, the displacement of water in the tank is 9/4 gallons of water. So another way of explaining that is to say that the amount of water in the tank increased by 9/4 gallons of water. So now in part D, we're asked how much water is in the tank at time t equals 10. And we have to have some initial, there must be a point in time where we know how much water is in the tank to be able to answer this question. So that was given to us. We were told at time t equals 4, there are 40 gallons of water in the tank. So at some point, I would come up with a variable. So I'm going to let A of t represent the amount of water in the tank. Actually, I should do an arrow instead of an equals, since those aren't literally equal. And so also, I know the derivative of A would be W in this case. So I can go back, and what I was given at t equals 4, when time t equals 4, there are 40 gallons of water in the tank. So that if I define my variable A for amount of water in the tank, well, A of 4 then is W. So one way to answer this question, because I think we'll need this at some point, is we could write an accumulation function for A. So for the amount at any time t, that's going to be the amount of water that's in the tank at when t equals 4, since that's our known, we know that's 40, plus the accumulation of change of the amount of water in the tank between that time 4 and any other time t. And then remember, if we write this like an accumulation function, we need a dummy variable. And so instead of w of t, I'm just going to use x. Okay, so this is now asking us to find a of 10. Well, a of 10 is a of 4 plus the accumulation of change from 4 to 10 of w of t. Okay, so from 4 to 10, let's see, we've got from 4 to 6, a positive 3 is our area. From 6 to 8, a negative 3. And from 8 to 10, that's what, 2 by 3, so that's a change of 6. So we said that when when t equals 4, a of 4 is 40. That was given to us. And then we're adding 3 plus negative 3 plus 6. Nope, plus negative 6, sorry. I keep forgetting that was below the axis. Okay, so 40 minus 6 is is positive 34. So at t equals 10, there are 34 gallons of water in the tank. So now, because we wrote an accumulation function in part D, we can just use that to answer the similar question we're asked in part E. So how much water was in the tank at time t equals 0? Well, I have a function for that now. So a of 0 is going to be a of 4 plus the accumulation of change from 4 to 0. Actually, sorry, when I replace the variable t with that number, I can now use my w of t dt. Okay, so we said a of 4 is 40. And now when we're calculating this definite integral from 4 to 0, we're no longer moving left to right, but we're moving right to left. So we need to know from 4 to 0, like what's the area between the curve and the x-axis, and then we need to remember it's negative. So we have to really do this by decomposing this square, or rectangle rather, into a semicircle and not a semicircle. So the area of that rectangle is going to be 3 times 4, so 12. The area of this semicircle atop has a radius of 2. So the area of the semicircle is 2 squared times pi divided by 2, so 4 pi over 2, or just 2 pi. So the shape that's left, this orange area, well, that's got to be 12 minus 2 pi. So the area of the rectangle without the area of the semicircle. Okay, so remember though, since we're moving from right to left instead of left to right, that's going to be a negative. So I'm going to multiply 12 minus 2 pi by a negative 1 out in front. So my area is really 40 minus 12 plus 2 pi, since that negative would get distributed to both the 12 and the 2 pi. So that is what, 28 plus 2 pi. And then again, that would be gallons of water. All right, lastly for part F, what is the maximum amount of water in the tank between t equals 0 and t equals 10? So again, we're asked an absolute max problem. We're asked to find the absolute maximum amount of A. And again, A is the variable that we had to define for ourselves. So I know to find critical values of A, I need to know where the derivative of A, which is W, equals 0. So if I go back up to my graph, the only place where W equals 0 is at 6. So W equals 0 when t equals 6. So in my table, my t values are going to include the endpoints of my interval and the critical value 6. And I'm finding the amount of water in the tank. So another reason we had to define this variable is when I make a table, I have to have something to put in that slot. So I've got to have something to represent the amount of water. Okay, so in part E, we just found that when t equals 0, that there's 28 plus 2 pi gallons of water in the tank. So when t equals 6, we could use our accumulation function and we could start with, we know when t equals 4, there are 40 gallons of water in the tank. And from 4 to 6, we're adding 3 gallons. So 40 plus 3 gives us 43. And then lastly, we already got our answer 34 in part D. Okay, so we know the maximum amount of water in the tank on the interval from t equals 0 to t equals 10 is 43 gallons of water, and this occurs at time t equals 6 hours.